Bismillahirrahmanirrahim. Dear student, I hope you are fine and doing well. Today, our lecture is about prime and related congruence equations. It is basically the continuation of our last lecture. Basically, our last two lecture were related with the uh, number theoretic basic fundamentals that are required in public key cryptography. So these are again our two lectures that are fundamentally based on number theory, and these definitions are required in public key cryptography. So let me introduce something that is prime related congruent class equations and some other ideas. Let us start today's lecture. The objective of today's uh, lecture is to introduce prime numbers and their cardinality and their importance in cryptography. Moreover, we will discuss some primarity test algorithm and their efficiencies. And since we are a bit concentrated on public key cryptography, so I will love it as an exercise, the how to find out the efficiencies of any encryption or what you call the efficiencies of prime testing algorithms. It is fundamentally related with big O and big theta notation, and it might be related with the computational complexity, and that involves time complexity as well as memory complexity of of fundamentally your algorithm. All these complexity theory is related with more or less related with what you call P hard, NP hard, and other related stuff. But we are not focusing on these complexity and number theoretic complexity of algorithm. So we are focused on cryptographic need of prime number in cryptography. So because our course is related with what you call the cryptography, and let us today today the objective of our class is right this on in this slide, but uh, which topic will be covered in this lecture, today lecture, basically related with the definition, cardinality of prime numbers, checking for primeness, then some number theory theorem like Euler phi theorem, Fermat little theorem, Euler theorem, and then how to generate prime numbers. Dear student, let us start with. These are some topics, and I just take this definition from chapter 10 or 9 or 10 of what you call the book of, let me give you the title, The Cryptography and Network Security by Frozen, its first edition by Rose Frozen. And then another chapter, Fundamental of Cryptographic Characteristics of Boolean Function, a review by Dr. Saida Irambatul and Dr. Majid Khan. And then Introduction to Information Security System, Cryptography and Information Security Approaches for Images and Videos, book, chapter, Taylor and Francis. So, these references are given at the end of this today lecture. So let us start with. So to topic of discussion in this section is definition, cardinality of prime numbers, checking for primes, Euler phi function, Fermat theorem, Euler theorem, and then generating primes. Let us, dear student, come up with three integers which are quite useful in cryptography. That is, first one is number one. That is exactly one divisor. It is only one number itself. That is one. That is prime, that it has exactly two zeros. It is divisible by itself and then unit element means to say one. Then composite number, it has more than two divisors. So it means composite can be break into product of prime. Uh, what is the smallest prime number? So the smallest prime number is 2 and it is divisible by itself and 1. So another example, list the prime number less than 10. That is 2, 3, 5, and 7. Uh, cardinality, I mean to say, what is the cardinality? How many prime numbers? There are infinite many prime numbers. So the cardinality of prime is infinite. So there is some lower and upper bound of prime numbers like this one. If I take this, find the number of prime less than this 10,000, how many prime numbers there will be. So I have to find out the what you call the upper and lower bound. So the lower bound is 72, 1,383, and upper bound is 78,543, and the actual number of prime is 78,498. So checking for primeness. Given a number and how can we determine is it prime or not? So we have to calculate its under root. And if after taking under root, if you have fraction values, so we have to omit the fraction numbers and take its rounded back. So, but this method is not so much efficient. But it is good for to start with from somewhere. So, but it is again inefficient method. So, if you can say this one, like 97 is prime or not. So I have to check like this one. I take under root of 97 and then there will be a fraction value and that's I omit fraction and I get 9. So the prime less than 9 are 2, 3, 5, and 7. So we need to see if 97 is divisible by any of these numbers. Uh, look, so it is not. So 97 is 5. So first we have to take under root of 9 and then we have seen the prime less than 9 is 2, 3, 5, 7. If among these prime, if these are divisible by these are divisor of 9, then in that case we can say the 9 is this is not a prime. 97 is not a prime. If this is not divisible by uh, 9, then we can say the 97 is prime. So in that case, if you can see 97 is divisible uh, by any of these numbers, like this one, to see that, but it is not like this. From these, we can say these 1, 2, 3, 4, 5 elements. Through we can say these are not. 97 is not divisible by 2, 3, 5, and 7. In that case, 97 is prime. So let us take another example. And floor of 301 is 17. We need to check 2, 3, 5, 7, 11, 3, and 17. So the number 2 and 3 and 5 do not divide 301, but 7 divide. Therefore, 307 is not a prime number. So first of all, you have to take the under root and then floor it. You will get 17, and then you have to find out the prime less than or equal to 17, and then you can check it out whether these prime which are less than or equal to 17 are divisible by can divide 301 or not. If it divides, then we can say these are not the actual number is not a prime. If this is not divide divide then in as in you can see in our previous example. So in that case, it is not a prime number, because 7 divides 301. In that case, we can say, dear student, 307 is not a prime. So, how many primes are exist in first 100 integer? So, in that case, you can see over here 2, 3, 5, 7, then 11, then 13, 17. So, how many are there? There are. So, there are probably 26 prime numbers in first 100 integer. So, in that case, there are 26 prime numbers. So Euler 5 function basically give you the number of unit element in any modulo classes, and this play a quite important role in cryptography. So Euler 5 function of 1 is 0, and Euler 5 function of p is p minus 1 is p is prime. Euler 5 function of uh, m cross n, where m and n are relatively prime, means to say their GCD is 1. In that case, you can take it phi of m into phi of n. If m and n, I means to say GCD relative to prime, I means to say whose GCD is 1. Phi of p power e is any integer, positive integer. So in that case, the student, for this the Euler 5 function is p to the power p to the power e minus p to the e minus 1 if p is prime. Let us take some example. We can also generalize these. If any number can be written as a product of power of prime, that is this one. Let me do it. This one. That is this one. P power p to the power e1 into p to the power e2 into p k to the power ek. In that case, we have found that phi of e is like this one. Phi of n is p1 e1 minus p1 e1 minus 1, as in our last case, fourth case. Third, we have basically combined third and fourth case. In that case, we individually apply this and multiply the product. In that case, basically this is more general case as compared to last four cases. So one can say the difficulty of finding phi depend upon the difficulty of finding the factorization of n. So let us take what is the value of phi of 13, because 13 is prime. In that case, phi of 13 is p minus 1 equal to 12. We have used like this one, the student who have used this case, second case. And what is the value of phi of 10? Say 10 is not a prime, and 10 can be written as a product of prime 2 into 5. In that case, the student who will use the perhaps third case of which is available on slide 11. So if you can see, 2 and 3 are relatively prime. In that case, phi of 2, I mean to say, since 2 is prime, in that case, we have used second case, which is p minus 1. It means p minus 1, it means 2 minus 1 is 1, and phi of 5, which is 5 minus 1, which is 4. Thus, 1 into 4 is 4, because 2 and 3 are prime. Another result is 240. It can be written as a uh, prime power product. It means 2 power 4 into 3 power 1 into 3 power 5. And in that case, we will use generalized case, which is placed on slide number 12. So in that case, you can see phi of 240. I mean to say Z240 steric. Unit element in Z240 is 64. There are 64 elements in Z240 was unit multiplicative inverse is possible. So can you say something? Phi of uh, uh, 49, it can be written as 49 can be written as a 7 into 7, and 5 of 7 is equivalent to 6, 7 minus 1, 6, and then 5 of 7 is again we will use the second case of Euler 5 function available on slide number 11. But does this result is valid? No, this is not a valid result, because if you can see over here, the third third result, uh, you can break n this one. Uh, this can be break if m and n are relatively prime. If you can say 49, phi of 49, phi of 49 can be written as a phi of 7 into 7, phi of 7 into 7, but in that case, here you can see 7 into 7. The 7 and 7 are not relatively prime, because the GCD of 7 and 7 is 7. So in that case, this result you cannot say the phi of 7 into 7 can be written as a phi of 7 into phi of 7, because 7 and 7 are not relatively prime. So, dear student, in that example, if you can see over here, you cannot write like this one. You can write only if these result and this is relatively prime. So we cannot write. So we will use fourth rule that is available on slide number 11. So phi of 49 is 7 to the power 2. It means minus 7 to the power 2 minus 1. It means 49 can be written as a 7 power 2, and it means phi of PE. Here E is 2 and P is 7. So we have used the fourth case of Euler 5 function. And so this is not correct. So we have to use this one. What is the number of element in the Z for static? I means to say static means to say unit element. So phi of 14, I means to say I have just break 14 into 14 into the product of primes. It is 7 into 2. So 7, phi of 7 is P minus 1 results. That is 7 minus 1, 6. 2 minus 1, which is 1. So 6. There are basically unit element are in Z14 is 1, 3, 5, 9, 11, and 13. And also the GCD of these unit element with 14 is 1. So interesting point is that if n is greater than 2, then value of phi of n, this is this one is even, is always even if n is greater than 2. So, dear student, these are some very good, important result of Fermat little theorem. What it says: if you have any number a and to the power p minus 1 is congruent to 1 mod p, is first version, and second version is a to the power p, which where p is a prime, is congruent to a mod p. These are quite important results, and these are very important due to the fact this is used in number of public key cryptographic crypto system in the correctness proof of what you call the public crypto system. So these results will be quite useful while you have what you call the give the proof correctness proof of your public key crypto system. So let us these are some results, so you have to keep this in your mind. And moreover, these are quite useful while calculating the inverse in modulo classes. So find the result of 6 10 to the power 6 mod 11. So in that case, if you can look over here, the first version of Fermat little theorem, that is P is 11. So in that case, uh, uh, if you can look over here, 6 GCD of 6 and 11 is 1, and this is 6 to the power 10 mod 11 is always 1, because if you can look over here, this is any element of ZP, and whenever I say mod P, it means I am taking element from ZP. So this is any non-zero element greater than 1. So if you can look over here, so the result of 6 to the power 10 mod 11 is 1. The moreover, the result of 3 to the power 12 mod 11 is 1. So, dear student, I have to do something that 3 power 10 is what you call uh, 3 to the power 10 is 1. So, I have to do is like this one. Here the exponent is 12 and modulus is 11 are not same. Uh, Not same with substitution. This can be solved using Fermat little theorem like this one. If you can look over here, so I have to break this 3 in 3 to the power 11 into 3. So 3 to the power 11 mod uh, 11 is what you call you can say this one. We have used second version of Fermat little theorem. Here we can also use the first fundamental first Fermat little theorem too. For that we have to use 3 to the power 10, but here we just classify 3 to the power 11 like this one. If you can go back to last slide, like a to the power p counter to a. And in that example, if you can see like wait for a while. In that example, 3 to the power 11 mod 11 is give you the result 3, because a to the power p is common to a. So in that case, dear student, if you can look over here, 3 to the power 11 mod 11, 3 in mod 11. So the result of this one is 3, and the result of this one is surely 3. So 3 into 3, 9 mod 11 is always 9. So for this, if you can see over here, through Fermat little theorem, you can solve this very big power of 3 to the power 12 easily. So one of the very good application of this Fermat little theorem is to find the inverse or mod p by in last classes we have used Euclidean algorithm or extended Euclidean algorithm in order to find the multiplicative inverses. So we can also find the multiplicative inverse by using Fermat little theorem, extension of one of the extension of Fermat little theorem. Like we have to use the mod 17. So we have to use the inverse of 8. Inverse of 8 mod 17. So inverse of mod 8 17 is a to the power p minus 2. 8 to the power 17 minus 2 mod 7. So 8 to the power 15 mod 7, and 8 to the power 8 to the power 15 mod 7 is 15. So the inverse of 8 in under modulus 17 is 15. So inverse of 5 under mod 23 is 4. So inverse of 60 under mod 101 is 32. So inverse of 22 under mod 211 is 48. This is quite good, and it basically reduces your computational complexity while developing it in the computer program. So, dear student, these are one of the application of Fermat little theorem. Another version, where, or you can say the generalization of Fermat-Little theorem, we call it as a Euler theorem, which is generalization of Fermat-Little theorem. That is, the first version of this is a to the power phi of n is congruent to mod n, and we can say this is useful for any composite number n, but the Fermat-Little theorem is mostly useful for prime, mod prime, but this is generalization. And second version is a to the power k into phi of n plus 1 congruent to a mod n. So you can say the second version of Euler theorem is used in RSA, uh, like this one. So we have any mod other than prime. So in that case, uh, 6 to the power 24 mod 35 is 6 to the power 5 35 mod 35. So 5 of 35 mod 35 is like this one. This one I have to use this. So another result, or to find 6 to the 20 to the power 62 mod 77. In that case, dear student, if you can say, take this one, phi of k is 1, uh, phi of 77 plus 1 and mod 77. So this is k to the power 1 I means to say, uh, 20 mod 17 and 20 mod 5 of 77 plus 1. In that case, our result will be 15. If you can look over here, dear student, this will be quite easy to calculate such a big power of any number, mod any composite number. So through this result, we can easily solve by hand calculation of any modular operation. Multiplicative inverses through mod and through this generalization of Fermat-Little theorem means that how you can use Euler theorem to find the multiplicative inverse under modulo a composite number. And previously we have calculated the multiplicative inverse under modulo prime, but here we have used a multiplicative inverse modulo a composite number n. So let us take one example. Uh, So inverse of 8 mod 70. 77 is what you call the composite number. So 5, 8 of 8 to the power 5 of 77 minus 1 mod 70 is 8 to the power 59 mod 70. This is 29. So let's these three part you have to do it by yourself. uh, Mersenne prime numbers. This is another, dear student, one of the shortest way to find the prime numbers. If you can put p is 2, p basically p is prime, to the power p minus 1. These are Mersenne primes, but this is not what you call all the time. It doesn't give you the prime. It may or may not be prime, but we can say this is Mersenne prime number if m2 to the power 2 to the power 2 minus 1, this is 3. Okay, this is prime. 3 3 to the power 3 minus 1, this is again a prime. But for 11, the 2047, this is not a prime because this can be written as this one. So similarly, it does not always give you the prime number, but it give you mostly prime number, but generally it may or may not be a prime. Another result is Fermat primes. This expression is p f n is equal to 2 to the power 2 to the power n plus 1. If F naught, 3, F1, F2, F3, but for F5, this is not a prime. Again, the Fermat primes may or may not be always give you the prime, but this is one of the way to generate the prime. So, dear student, these are some of the references from where I have taken some these from where I have prepared my lectures. The most important one is Cryptography and Network Security by McGraw and Hill, the book by Barros Frozen, and then another book by Taylor and Francis by Dr. Majid Khan and Sayyida Rambatul Naqvi, and then another book chapter from Taylor and Francis, that is cryptography and information security approaches for images and videos. Book chapter, one of the book chapter, and publisher Taylor and Francis in 2018 and 19, and it is published in CRC Press. Till then, Allah Hafiz, please stay at home. May Allah bless you all. Allah Hafiz.